Hello, I'm Jenny Grosslight, here to demonstrate how you can obtain signal integrity insight from the Agilent U4154A state mode logic analyzer. This demonstration will focus on examples of gaining signal integrity insight from iScans. To obtain iScan information, go to the sampling icon on the overview screen, open the iScan and sample positions and threshold window. All tabs correspond to different signal groups. Currently, we are looking at the address and command signal group. We are viewing iFinder and iScan information. So when I grab the threshold bar on RAS and move it up or down, if the iFinder I corresponds to the threshold level, normally you will use the threshold that is automatically determined by the system. You will change to the scan-only mode. The scan mode is particularly good for observing rising and falling edges. Color intensity helps you see where the most activity occurs. All scans are relative to the 0 point, which is the clock edge that is clocking the logic analyzer. For DDR3 measurements, 0 equates to CK0 rising and falling edges. That is why on the address and command lines, we do see activity relative to the falling edge. Next, we'll move to the read data group. One of the first things you'll notice is that these eyes look relatively small. And that's true. At DDR3 2340, the eyes captured from an interposer are very small. The U4154A is the only logic analyzer capable of capturing any DDR3 data from any probing over 1867. The power of bus-level signal integrity insight is being able to scroll through all of the signals in a group relative to each other and to identify signals that need to be addressed with a scope. We are scrolling through all of the read eyes. These eyes were scanned only during valid read bursts. The 0 point is relative to the closest edge of CK0 after accounting for the cast latency. By comparing all of the eyes, we see the byte lane shift, and we notice that the eyes get slightly smaller on byte lane 1 than they were on byte lane 0. Continuing to scroll through, we can notice that byte lane 2 also has smaller eyes. As we get through byte lane 2 and into byte lane 3, we will notice that the eyes open up. These eyes represent sampling in the overlay mode, where each of the samples is scanned in for the number of valid clock cycles for read bursts. Each of the 8 samples in a burst are overlaid on top of each other to provide one eye that is the composite of all 8 samples, not just for one burst, but for as many bursts as we dictate by the number of clock cycles we scan for. As we had scrolled through, we noticed that byte lane 1 and byte lane 2 had relatively smaller eyes compared to the other byte lanes. Scrolling down to the strobes, we can understand more of that byte lane closure. Watching the strobe eyes, their sample positions will relate directly to the read byte lanes. We see DQS0 has a shaped eye than DQS1 or DQS2. Scrolling down to DQS3, we see it has an even larger eye. Since the data is driven from the strobes, this makes sense that what we really would want to look at with our scope is the behavior of the strobe from the DRAM associated with byte lanes 1 and byte lane 2, as they have the smallest eyes. Check out the links listed for more information on Agilent products and DDR solutions.